Hey guys, welcome back to another maths interview practice style video. And in this video, we did question 1 in the previous video, so I'm going to do question 2 in this video. And yeah, I'm going to give myself a timer of 25 minutes. And after that, if I manage to complete the question, I'll check the answers. Otherwise, I'll look at the solutions and do it, all while trying to explain my thought process as clearly as possible. So let's just add this in over here. All right, yeah, and let's start the timer. There we go. All right, so question saying, the power set is formed from all subsets of a given set. If a set contains n elements, what is the cardinality of its power set? So first of all, let's just explain what cardinality is. Fairly sure it just means how many items are in the set. In a set. So if we had a set like 1, 2, 3, then you could say the cardinality of this set was 3. So again, I guess this is split into two parts, and let's consider each part separately. So let's say a set contains n items, and I'm just going to call them 1, 2, 3, 4 up to n. And we want to find out the cardinality of its power set. Okay, so immediately I'm thinking it's going to be a different answer if the elements aren't unique. So if they're all unique, then we're going to have one answer. But let's say we had 2 1s and then skipped the 2, then went n. So this could have a subset of 1, but it can't have a subset of 1, 1 because a set has to have unique elements. So that doesn't count. Whereas if we had this set, this would have 1 and it would have 1, 2. So by making the elements not unique, we'd end up with... Sorry, I just realized that's a silly thing to do because you can't have a set containing non-distinct elements. So if it's a set of n elements, that implies that all elements are unique. All right, yeah. So let's say this is our set. Now, we want to count how many different ways there are of making a subset. So, okay. Let's think about this. So, number of subsets. And I think one way we could do this is considering a bunch of different cases. So we can split the number of subsets into number of subsets of length 1 plus the number of subsets of length 2 plus the number of subsets of length 3, on and on until we get to the number of subsets of length n. And this final case is easy because it's just going to be, there's only one subset of length n and it's the original S. So let's see if there's some kind of pattern we get when we look at each of these cases. So let's look at case with length equal to 1. So here we're trying to construct a subset, I'm just going to call it sub, which only has one element. And clearly, that element could be anything from the original set, like so. So I guess this has n subsets, right? Because to make a subset of length 1 from this original set, we just have to pick any element from this set. Okay. Let's think about the case with length equal to 2. So now we have, I'm just imagine this is the set. We have to put two different elements from S into this set. Let me just color it in S a different color so it's easy to come back to. Put it in purple. Okay. So we could either put a anything from S, and then we could put S minus the original one. So as an example, here are our options for the first set, first slot, and then here are our options. Let's say we pick 2, then we would just skip the 2 and have our second option. So for this first slot, there are n options, and for the second slot, there are n minus 1 options. Okay. Let me just think though, because that would imply there are n times n minus 1 subsets of length 2. But we also have to remember that order doesn't matter. So let's say we constructed our set like this. So we said we picked 2 for the first one and 1 for the second one. So this is one subset. I'll put this in red. So here's one subset we've picked. And let's say we chose a different selection. We chose 1 and then 2. Clearly, these are the same set because they contain the same element, and sets are unordered, so we don't care about the orders. So they contain the same element, same number of elements, so it's the same set. But with this, we would end up counting these as separate sets, and that's not what we want. So we need to make sure we also divide it by the permutations, the number of possible permutations of these slots. Subsets of length 1 when considering order. Let's just say that. Therefore, I'll say n minus 1 over 2 factorial, because there are 2 factorial permutations of these slots. That's just the same as 2 factorial subsets of length 2 when not considering order. Okay, there we go. So I guess we can use a similar sort of strategy. Let's now consider subsets of length 3. And you'll see this is a similar sort of thing. So we have n options for this first slot, n minus 1 options for the second slot, and n minus 2 options for the third slot, because we've already picked 2 options. And then we also have to divide it by the number of permutations, because let's just say we picked 1, 2, 3 as one subset. We might pick 3, 2, 1 and even 2, 1, 3 or 2, 3, 1 as different options. These are all the same thing, all the same subset, but using this slot method, these would be considered different. So we have to divide all of the number of total different permutations or sequences by the number of rearrangements of each permutation. So we'll say, therefore, n minus 1, n minus 2 over 3 factorial, because there are 3 factorial or 6 permutations. I'll say arrangements. I've been using permutations too much. 3 arrangements of each subset, which doesn't make much sense because sets don't have arrangements, but just I guess assume it's true. And you can see these would be the different arrangements, like so. And every single one of these is the same set, so we have to divide these out let's say for every set of 3 numbers, there's going to be 6 different options, and we have to divide that out. That's why we divide it by 3 factorial. So that is the number of subsets of length 3. And yeah, hopefully you can see, hopefully this pattern just continues. I think it should. So now let's write out our thing again. Number of subsets, that's equal to the number of subsets of length 1. And I'll write it as n over 1 factorial plus number of subsets of length 2 over 2 factorial plus the number of subsets of length 3 minus 2, 3 factorial, bang, 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 all the way up to the number of subsets of length n, which is going to be, if we just continue this pattern, n minus 1, and that would just simplify to 1 over n factorial. And we can see this is actually just n factorial, which simplifies to 1. So now we have an expression for this number of subsets. We just need to figure out a way of simplifying this. And I think this actually looks really similar to the binomial expansion. Remember that 1 plus x to the n is equal to 1 plus nx plus n minus 1 over 2 factorial x squared plus n minus 1 n minus 2 over 3 factorial x cubed, going on and on. So this looks really similar to that. And I wonder if we can sort of map this or match this by selecting an x, which makes this identical. So notice that we're only interested in the coefficients of x, and the x's, they don't seem to have an effect at all. So if we decide to set 1 plus 1, if we set x is equal to 1, then notice what happens. We're going to get n times 1 plus n minus 1 over 2 factorial times 1 squared plus n minus 1 n minus 2 over 3 factorial 1 cubed, all the way until we get to n minus 1 n minus 2 1 over n factorial x to the n. And the next term would have a 0 in it, although this is an infinite expansion, but next time would have 0 and all subsequent terms will have 0. So they cancel out. And yeah, you can see the 1s essentially will just disappear because that should be a 1. Be a 1 there. And it will just disappear because 1 to the power of anything is 1. So yeah, we're able to use this formula now. So we can write the number of subsets is equal to 1 plus 1 to the n, which is equal to 2 to the n. And there we go. That is basically it. Now I wonder if there's actually an easy way of representing this. So let's say we have, this is our set. And I suppose an easier way of getting to this answer would be, for each element, it's either in or not in the subset. So we just go along and select whether the elements are going to be in the subset or not in the subset. And for each selection of these, whether it's in or not in, that forms a unique subset. So we have 2 choices for each element because we either add it to the subset or we don't add it to the subset. So that ultimately leads to number of subsets is 2 times 2 times 2 n times, which is equal to 2 to the n. So yeah, I guess that's a simpler way of getting to it, but I think my way, or my original way, was a bit more clearer and forms a bit more of a nice way of seeing it. Actually, no, this way is definitely nicer, but yeah. Oh well, let's move on to part B. How many subsets contain a given element x1. All right, so let's try and answer this second bit. So now let's define our set to be x1, x2, x3, x4, and I'll actually just call them 1, 2, 3, 4, all the way up to n. You can just imagine these as having x, and then these are just the subscripts, but it's just easier to imagine it like this. And now it's asking us the number of subsets which contain a given element, and we can really pick anything because of the symmetry of this. So we'll just say the number of subsets with, we'll say, containing we'll just say 1. Okay, now I feel like there's a very nice way to see this. Let's try and think about it. Okay, so what I'm thinking is, of these original all of the subsets, half of them are going to contain the 1 and half of them aren't, because if you imagine for the power set, all subsets of S, within this, there's going to be, for every set, there's going to be one set which contains 1, paired with one set which has all the same elements but doesn't contain 1. Because this contains every single subset of S, there's going to be one of these for every single set, I guess, within this. So what that means is exactly half of all subsets contain 1, and then that means we can just half our answer to before, which is going to be 2n over 2, which is 2tn minus 1. And I think it's nice to see it using this sort of method as well. Let's see, our original set S is 1, 2, 3, 4, 5, up to n. So the previous question, part A, was just concerned about getting all the subsets, so we just decided whether we wanted to include or not include every element. This time, we can think about the 1 is always going to be included, so that's fixed, but then for every other element, we can either choose to take it or accept it. Sorry, take it or reject it. And so we have one choice for this first element, x1, and then 2 choices for everything else. So that's going to give us 2tn minus 1 times 2tn minus 1 multiplied by 1. And notice that it doesn't really matter what element we pick. Like, if it was the 4 which we needed to add, then we would have only one choice in a 4. It's always in it, but then the 1 would get 2. So the numbers get shuffled around, but the multiplication ends up being the same. So there's the answer to part B. We'll say it is 2 to the n minus 1. Okay. And yeah, that seemed like a relatively simple question. And yeah, let's see whether we got it right. Let's see what timing as well. Okay, so we have 6 minutes left, pretty good. And generally it's quite concise answers, so let's just see whether we got it right or wrong. And I'll write, this is the answer to part A. Okay. The size of a power set is simply a power of 2, power being the number of elements, so yeah, 2tn, as each element is either included or excluded within the subset. Okay, good. And the number of subsets containing a given element is the previous power of 2, as we can imagine, forming every possible subset without the given element, and then include it in each. Right. Let me just have a look. A given element is the previous power of 2. Oh, okay, so the previous power of 2. Okay, so 2 to the n minus 1 compared to 2 to the n. Okay, yeah, so those seem like the correct answers. And yeah, I'd say that was a pretty well executed question. You can also see how they sort of thought about it. You can imagine. Okay, so we're choosing. Okay, yeah, so for each element, I guess once we've included one, we're now choosing if we split it into cases. So, oh yeah, that was actually an easy way of seeing it. In each case, if we go back to these over here, like with a case of length 2, that's literally just choosing 2 items from the set. So it's going to be n choose 2. And case of length 1, that's going to be n choose 1. Case of length 3, that's n choose 3. So overall, that would give, the answer would be n choose 1 plus n choose 2 plus n choose 3 all the way up to n choose n. And that's a famous identity, I'm fairly sure. But yeah, I guess that ends up with 2 to the n. Also because if you remember on Pascal's triangle, the rows add up to powers of 2, which is fairly interesting. But yeah, that was a interview question complete. The power set, cardinality of the power set. Thanks for watching. Hopefully this explanation kept you along and you're able to follow. Thanks for watching. See you guys in a future video. Bye.